Good afternoon. My name is Seth Brooks, and I am a PhD candidate at Syracuse University, working with my advisor, Dr. Melissa Green. And today I will be talking about the locomotive performance of a 2 degree of freedom fish model. The motivation for this work comes from the desire to better understand underwater propulsion. And if we look at current underwater vehicles, we see that they're typically designed for a single mission and fall into two major categories. The first is the long, slender, torpedo-like vehicle that we see on the right. We have a single screw propeller, and these are extremely efficient at going fast, but they're not very maneuverable. On the other hand, you have the box-like inspection style underwater vehicle shown on the right as well, that typically has multiple screw propellers and is very maneuverable due to these multiple propellers, but it's not very fast, and because of its shape, it's extremely susceptible to any flow disturbances. And so I want to bridge these two divides and look at oscillatory propulsion and see if we can find a new method of propulsion that can work in both these situations. And so our objective is to look at biology, specifically fish, and understand how they can swim while being fast, maneuverable, and efficient, and use this to guide future vehicle design, whether that's geometry or controls for a given geometry. So I'll be looking at three major things in this. The first is determine what are the optimal kinematics for a given geometry that allow for maximum thrust or maximum efficiency. I also want to look at large-scale parameter trends. So once you have a fixed geometry, how can you adjust your parameters to slightly change your desired output, whether that's more thrust, higher efficiency, longer duration of motion. And finally, there's a large body of literature that looks at pitching and heaving airfoils as a simplified model for these complex three-dimensional systems. And they've come up with a lot of trends and outcomes from that. And so now that I have this complex three-dimensional model, I would like to look to see if the conclusions and trends that were developed on these simple models can be extended to more complex three-dimensional systems, such as the model in this work. To talk about the model, I will talk about two main sections. First, the geometry on the right, and then the motion on the left. For the geometry, the model is composed of three main sections. We have the head at the front, and this is the blue region, and it remains stationary for all cases. Next, in the middle, is the yellow region, or the tail, that spans from the sting at the central point of the model to the peduncle, or the narrowest part of the model near the rear. And this is the first degree of freedom for the motion. Next is the caudal fin, or the red region, and this is the second degree of freedom for the model. And these relate very closely to the biological inspiration, or yellowfin tuna, shown at the bottom. Now looking back on the left, we have the motion description. This is all the parameters outlining what they are and their directions. But basically, we have three main parameters. We have A, which is the maximum trailing edge excursion of the caudal fin. And this is how much the trailing edge of the caudal fin moves laterally. We have phi, or the phase offset between the 2 degrees of freedom, the tail and the caudal fin. A positive phi means that the tail leads the caudal fin by this amount. And finally, H star, this is the heave to pitch ratio. So if we compare this to simpler models of a pitching and heaving airfoil, this is where I get the heave to pitch analogy. So an H star of 0 means that there's no heave, it is all pitch. And in this case, an H star of 0 means that the tail is stationary and the caudal fin pitches about the peduncle. So all of the trailing edge amplitude A comes from pitching of the caudal fin. An H star of 1 means that we have pure heave of the caudal fin. And in this case, the caudal fin remains parallel to the free stream and moves laterally due to the oscillation of the tail at the leading edge of the caudal fin. Now on the right, we see the scale of the model. The caudal fin has a chord of 100 millimeters, a span of 200 millimeters, and a leading edge angle of 45 degrees. And the whole model has a length of about 540 millimeters, with the tail composing roughly 158 millimeters in the center. Now on the bottom are the bottom describes the parametric space that I'll be looking at. We have the motion frequency F, which is fixed at 1 hertz. We have a free stream velocity fixed at 210 millimeters per second, and the trailing edge excursion we talked about previously, A, ranges from 25 to 115 millimeters. The heave to pitch ratio varies from 0 to 1, and the phase offset ranges from -20 to 150 degrees. These result in non-dimensional values for Struhl number between 0.12 and 0.55, so that extends past the biological range of the 0.2 to 0.4, and the Reynolds number is in the range of 10 to the fourth, 10 to the fifth, depending on whether you look at the chord length or the total length of the model. And now we'll discuss how I put the model into the test apparatus and collected my measurements. So first, the model was mounted to a carriage above our water tunnel that runs on air bushings that allow for near frictionless motion in the free stream direction. And all the data is going to be phase average or time average. So in order to phase average, I use rotary encoders on the two motors that control the 2 degrees of freedom. And this allowed me to link all my measurements to a position of the motor and easily phase average. I then got my power input by measuring the torque in line at each of the motors. So I have 2 torque sensors. I measured my power output or thrust using a load cell, which is mounted between the tunnel and the air carriage. And finally, external to the water tunnel is a linear displacement sensor. So this collected point measurements either on the caudal fin or on the tail. And with the known sting location, I can back out all of my motion parameters to ensure that my prescribed motion matches what my actual motion was. And now a little bit more detail about each of these measurements. So my power output, my power input, my efficiency. And so first, the power input. This was the torque measured in each motor. So I did this instead of looking at electrical power. So what I did is measured the torque at each of the motors when the model is operating in the case conditions in the tunnel with the water running, and then I measured it in the air, so the model external to the water. And this allowed me to subtract out the inertial effects and the efficiencies due to the power transmission from the motor to the actual model. I converted this to power by multiplying by the angular velocity of the motor, which I got from the encoders, and then converted it to a coefficient of power as shown here. Next, the power output. So this is the streamwise force that the fish produces. All of my measurement, well, the measurement of my load cell is the net thrust, but I'm really interested in the thrust production. And so I borrowed this method from ship design where you have a hull efficiency or a hull drag that you subtract from your net thrust. So I used this first order approximation where I said my dynamic drag is roughly equivalent to my static drag. I know it's not great, but it's a first start approximation. So if you put the model in the tunnel with it not moving, but the water is running, and you take a time average drag that's produced, I then associated this with all of my cases and subtracted that from the net thrust to get the true thrust that's being produced, multiplied by the free stream velocity to get a power output, and then shown here converting it to a coefficient of thrust. And finally, quasi-propulsive efficiency. So this goes along with that approximation for power output. Once again, this is borrowed from naval ship design where you have a hull efficiency where you can subtract out the hull drag. And so the efficiency is the time average power output divided by the time average power input. And on the right are some plots showing the phase average results for each of these quantities. We've got the two degrees of freedom, the torque input, the thrust output, the air, the water, and finally the converted instantaneous phase average power at the bottom. We will now look at time average results. And before looking at the plots, I first want to show how each of the different parameters visually look as they are independently varied. And this will give you an idea of what it means when we look at the changing parameters and how it affects the performance outputs. And so first we'll look at the maximum trailing edge excursion A. And here are 3 animations that show increasing A from 40 millimeters to 100 millimeters. And in each of these videos, the dashed line represents the excursions of the trailing edge amplitude, and the dotted line, or the inner one, shows the maximum excursion of the peduncle region. For each of the 3 motion parameters, we'll look at 3 different outputs. We have the coefficient of thrust, which is the scatter plot on the left, the coefficient of power in the middle, and the quasi-propulsive efficiency on the right. Each point represents a case, and then it's colored by one of the other parameters. So in this case, we're looking at amplitude, so it's going to be colored by H star because it plays a role in the trends that we see. The first trend, looking at the coefficient of thrust, we see that for small H star values, so those are values less than 0.1, so this is basically pure pitching, we get a local maximum in thrust around 85 millimeters. And if we look at H star values greater than 0.1 all the way to 0.1, we see a monotonic increase in thrust as we increase amplitude, which is what we'd expect to see. You increase the amplitude and you're going to expect more thrust, not necessarily anything else, but more thrust will be produced. Next, looking at the coefficient of power, we have a monotonic increase in power as we increase amplitude, and with efficiency, we do have a monotonic decrease with increasing amplitude. And all three of these are generally agreed upon within the literature of pitching and heaving airfoils. Now looking at the phase offset phi in degrees, we once again see three different animations that show a fixed amplitude in H star and varying phi from 30 degrees to 120 degrees. And here you can see how this parameter changes what the kinematics and the motion look like in the system. Now looking at the time average result for the phase offset phi, we have the same three plots, but this time they are colored by trailing edge amplitude A, where a light color represents a small amplitude and a dark color represents a larger amplitude. And looking at all the data sets together, it is fairly easy to see the trends in the coefficient of thrust and the efficiency. And for both of these, there's a maximum somewhere in the range of between 90 and 115 degrees. But if you look at the coefficient of power, looking at all the data together, it's a bit more difficult to really see any sort of a trend. So we'll look at a single case where the amplitude, or a single amplitude around 100 millimeters, and we see that just like the thrust and efficiency, there is this optimal value with phi between 90 and 130 degrees. It's a little bit wider than the other two, but in general, it's the same area, just with a phi just larger than 90. So now what does the literature say? A lot of the literature suggests that thrust and efficiency are maximized when phi is equal to 90, and a lot of the current literature even just assumes that 90 is ideal based on previous literature, and they don't really look at phase offset. There is some literature as shown here that suggests that the optimal thrust and efficiency aren't at the same phi value, but usually one of the two is at 90 degrees. And so this data set suggests that thrust, power, and efficiency have optimal values greater than 90, and that 90 may not be the best option going forward. So we really need to look at the influence of the phase offset. Now looking at the heave to pitch ratio H star, we look at three different values ranging from 0.1 to 0.9. So 0.1 is basically pure pitching in the sense of an isolated propulsor, and H star equals 0.9 is close to pure heave. And these animations can help you visualize what it looks like as we vary this parameter. Now looking at the output plots, we need to look a little bit deeper than looking at all the cases together. So in order to do that, I will look at two different cases, one with a small amplitude, so the pink line of A equals 30, and one with a large amplitude, so A is equal to 100, to outline these trends and the continuous nature of them. And so first, we see that for all three cases, a small amplitude motion, so this is the pink line, the optimal H star value is lower than when you have a large amplitude. So this is the black line across the board for all three of these output metrics. So for coefficient of thrust, the optimal value changes from around 6.4 to 0.78 as you increase amplitude. For power, it's from 0.43 to 0.67, and for efficiency, it goes from 0.43 to around 0.73. And so let's compare this to the literature. The use of H star is relatively new. A lot of the older literature looks at heave to chord ratio instead of looking at the comparison between the pitching and the heaving motion. Some of the literature just talks about pitching and heaving together is better than either separately, which our data does agree with. And some very recent papers out of Lehigh University agree that the optimal H star value does depend on the amplitude, but we disagree on the optimal values. Their values range a little bit larger, so that for with small amplitude, it's a lower H star than what we show, and for a larger amplitude, it's higher than what we're projecting as the optimal value. We'll now look at the phase average results. So how do the thrust and the power vary along each of the cycles? So this is from a non-dimensional time frame, so from 0 to 1. And we'll look at two different plots. The plot on the left is the phase average results per cycle, and the plot on the right is relating these phase average results to motion parameters. And so this scatter plot shows the heave to pitch ratio horizontally, and on the vertical axis we have the timing of the peak thrust, and they're colored by phi. And so the coloring is the same between these two plots. And so if we go back to the left-hand plot, which shows the phase average results, we see a bunch of curves, and I've highlighted a thrust peak here in green. So this is for a small phi value. And as we increase phi, I will highlight each of these peaks, and we see that it starts here in the low region around 0.1, and then it jumps over and goes to this 0.2, 0.25 region. And if we look over at the scatter plot again, we can see this again. There's a transition here from around 0.1 up to 0.24 as we increase the phi value. So this highlights what the plot on the right is representing. And so now we will look at some of the results from this. We will use these two plots to highlight how the phase offset phi and the heave to pitch ratio H star relate to the timing of the power output. So this is the thrust power. We'll do that with the two sets of plots. On the upper right is the scatter plot with H star on the horizontal axis and the timing of the power output peak on the vertical axis. And at the bottom, we'll expand on these time average results to look at the phase average results. So we have 4 plots, each representing a different H star region at a fixed amplitude, so in this case 70 millimeters, and then colored by phi. So we can look at what the scatter plot looks like in the phase average sense. There are 3 main trends looking at the power output peak timing. First is that for moderate H star values, so this is from 0.2 to 0.8, there appear to be 2 peaks that are present for most phi values. And we see that the scatter plot on the upper right, I've highlighted this lower peak, earlier peak in the pink, and the later peak in the darker red value. And the second one is related to this, that as you increase phi, there appears to be a smooth transition where from the earlier peaks, the pink line being dominant, to the darker red lines, the later peak being dominant. It doesn't appear that there is a smooth transition where a single peak shifts from one timing to the next. It more appears that there are 2 separate peaks, that in these moderate values, both peaks are present, but one is more dominant over the other. There is some slight shifting, which we can see with these middle dots, but it does appear to jump where you have this earlier peak, this transition period where both are present, and then it jumps to the later peak as you increase phi. And you can see that a little bit better in the phase average results at the bottom. For these 2 middle plots, you can see that with the lighter red, there's this earlier peak, and as it gets darker, you get these 2 peaks in the middle, and then with the dark red, or the large phi value, you have this very prominent single peak that's later in the cycle. And the third trend is that the influence of the phase offset phi increases as you increase H star, which just makes sense because at a low H star value, the tail doesn't move. This is pure pitching of the caudal fin, and so the phase offset between the two doesn't have much effect because it's really a 1 degree of freedom system. But as you increase the H star, your tail becomes more important, and so the phase offset between the two also becomes more important. For the phase average plots on the bottom, if we now change the coloring from phase offset phi to the efficiency, we can see that specifically for these middle 2 plots that the highest efficiency for each of these H star values falls on a phi that's not at either extreme. So not with either of these peaks being dominant, but rather somewhere in the middle. And we notice this because both of the peaks are light color, which means they're low efficiency, and that region in the middle is where we have the dark color or the higher efficiency cases. We can now look at trends between the input power and the output power by looking at the peaks for each of these and then plotting them with the input power on the horizontal axis and the output power on the vertical axis, where if these peaks line up temporally, they'd be on this 1-to-1 ratio or the dashed line shown here. And each of these points is colored by their quasi-propulsive efficiency, where a light color is a low efficiency and a dark color is a higher efficiency. And the plots in the bottom are very similar to what we saw before, where the upper row is the power output and the bottom row is the power input. Using these plots, we see three major trends that relate the timing of the peak input and output power. So the first one is that looking at these two rows, we see that the input and output power have very similar shapes across the cycle, and that for moderate H star values, so these two middle columns, we do see that same split, so the earlier peak and the later peak. Second, looking at the plot on the upper right, we see that efficiency improves as their alignment becomes better. So as these dots get closer to the 1-to-1 relationship, so that dashed line, the efficiency also improves. And finally, the third is that the peak power input almost always occurs after the peak in the power output. This seems counterintuitive, where you'd assume that you would put power into the system, you'd maximize your input power, and then as a result, you'd get a peak in your output power. But this data actually suggests the opposite. In conclusion, I created a fully functioning 2 degree of freedom fish platform for investigating oscillatory swimming. The modular design of this platform allows for many easy geometric changes, as well as having full control of both degrees of freedom. The same platform can be used for acquiring power input and output, kinematics, and PIV measurements. The coefficient of thrust, coefficient of power, and quasi-propulsive efficiency were measured for 567 cases for the purpose of investigating the transportation performance of this model. When looking at the time average performance, the coefficient of thrust was maximized when the phase offset phi was between 90 degrees and 115 degrees, and when the heave to pitch ratio, or H star, was between 0.64 and 0.78. The efficiency was maximized when the phase offset was between 90 degrees and 115 degrees, and when H star was between 0.43 and 0.73. These trends do not match the existing literature on pitching and heaving airfoils, which suggests that more investigation is required. When looking at the phase average results, the power input and power output curves had a similar shape and had a split peak where there was an earlier peak and a later peak, suggesting two different mechanisms. And these peak timings were highly dependent on the phase offset and the heave to pitch ratio. The efficiency was optimized when the peaks in the power input and the power output aligned temporally. My next steps will be to perform stereo PIV along the caudal fin and also in the near field wake behind the caudal fin for two different purposes. One, taking single plane data over a majority of this parameter space, which will allow me to pinpoint what the leading edge vortices, the trailing edge vortices, and the flow, what it's really doing over a large parameter space. And then for select few cases, I will perform multi-plane PIV to reconstruct the full phase average volume to really see what all of those features are doing throughout the cycle. And all of this will be to investigate the relationship between the caudal fin leading edge vortices and the transportation performance. And so this will be a continuation of the work that I presented in my 2019 biomimetics paper. Thank you for your time.